All right, so today we're going to look at a really pretty packed section. It's going to take every bit of the whole period to do this section. So we're going to look at polynomial functions and their graphs. Let me see if I can get it a little better focused. It's a little bit better. So first let's talk about what a polynomial is. Poly means many. So I think we've already talked about polynomials just in general, just a little bit. But it's basically a function with one or more terms. And the qualification for it to be a polynomial is it has to have positive whole number exponents. So it's a very general category of equations because it could be squared, it could be to the first power, it could be to the 10th power. So the gist is really just any positive whole number exponent type expression would be a polynomial. So here are some examples of things that are polynomials. Some things that we've looked at this semester and some that we haven't quite yet. So linear functions are polynomials because what's the exponent in a linear function like this one? What's the understood exponent since I didn't write one? 1, right? Quadratics are also polynomials because the power is 2, right, which is a positive whole number. But what we're going to start looking at today is things with like higher powers than that maybe. So this 5th power expression is also a polynomial. We won't spend a whole lot of time, but I'm just trying to make a point. Even this funky numbered expression is still a polynomial. Notice there's a square root of 3 in there, there's a fraction in there, but what's true about the exponents that has to be true for polynomials? They're positive whole numbers, right? So the gist is I'm trying to make a point that they can look like a lot of different things. So some things that are not polynomials, that don't fall under the category of what we're going to learn about today, but we will talk about this semester, is anything with a square root is not considered a polynomial. Okay. By the way, the reason for this is because we talked about this when we looked at exponents, but this is the same as -5x to the 1/2 power. So it is not a positive whole number exponent, right? It has a fractional exponent. Something else that we're going to talk about this semester, but again, just not today because it's not a polynomial, is something where x is in the denominator in any form or fashion. But that is because this is the same as a negative exponent on x. So if x is in the denominator, it means you have a negative exponent. In other words, you don't have what kind of exponents that we're looking for. Positive whole number exponents, right? So a good rule of thumb is just to think of it like this. There's no square root. There's no x in the denominator. There's no absolute value. We didn't really talk about that, but nothing extra or fancy, basically. It's just plain old x cubes, x to the 5th, x to the 10th, those kinds of things. So these graphs, depending on what power they have, are going to have much different looks from what we have been graphing. So far, we've only graphed lines and parabolas, and so these are going to be different, but there are some common ground qualities for all polynomial functions. Okay, so the first one is they have smooth curves. So they are not like jagged edge type graphs. So I like to say there's no sharp edges. So remember when we looked at like the absolute value graph and it was a V? That would not be a polynomial because it's got a sharp edge. It's not curvy. And the second thing is that they should be continuous. And that just means just probably what you think. It just continues on. There are no breaks or jumps. No holes in the graph, nothing like that. So here are some examples of polynomial graphs. And we're going to talk about how to tell what kind of graphs we have. This would be a polynomial graph because it's curvy and continuous. But so would this, because it's what? Also curvy and what? Continuous. Okay, so just know that these polynomial graphs are going to vary from each other, okay, but they're always going to be curvy, they're always going to be continuous. So kind of like we did with linear equations and quadratic equations, we're going to break down all of the pieces of a polynomial graph in order to be able to kind of graph it by hand. That's kind of our goal. So there are going to be some terms we're going to talk about today that you may or may not remember from another class. So the first one is the leading coefficient. A coefficient is a number in front of a variable. Okay, so the leading coefficient is the number in front of the variable with the highest exponent. It doesn't necessarily mean it's the one in the front, but often it will be the one in the front. Okay, so because I'm lazy, I'm going to call this the LC from here on out, but LC means leading coefficient. What is that number in front of the biggest exponent term? So let's say that I give you this polynomial, 3x to the 4th minus 5x to the 6th plus 3x minus 10. That first exponent is supposed to be a 4. It's just not written very well. So I'm going to rewrite it so it looks better for any notes that I'm scanning. Okay, so if I asked you to find the leading coefficient, you would not just jump and say, oh, it's 3. Okay, that is the one in front, but which one's the one in front of the highest exponent thing? -5. So the leading coefficient's actually -5. Okay, notice if we would have written the terms in order like we normally do, we should be starting with highest exponents first. But we didn't, okay, so the leading coefficient there would be 5. So something else we're going to need to break down from a polynomial function, not just the leading coefficient, but also the degree. And the degree is just the highest exponent of a polynomial function. So the leading coefficient is the number in front of that highest exponent, and then the degree is the highest exponent itself. Okay, so in the above example, the one that we just looked at, what would be the degree? 6, right? So we would literally call that a 6th degree polynomial. Because we call first powers linear, we call second powers quadratics, and we call third powers cubics, but after 3 we don't really have a word for it, like we don't do a quad something for 4 or anything like that. So for anything higher than 3 we just start listing the number. Okay, so this would be a 6th degree polynomial, which all that means to you is there's the highest power is 6. Okay, so one thing that we want to know when we're trying to figure out what a graph looks like, and that's what we're going to practice today, trying to figure out all the puzzle pieces to what the graph is. And so the first thing we like to know is what the end behavior is. And if you kind of read that, it's just like what it sounds. It's what the graph is doing at the ends. Or it's what the graph is doing at the far left and the far right. But that's just a fancy way of saying at the ends. Okay, the end behavior is not really concerned with what the graph's doing in the middle, just what's it doing on the far left, and then what's it doing on the far right. So before I show you kind of how you can pick out the end behavior based on what a polynomial looks like, I want you to kind of sketch 2 graphs with me, and we're going to talk about the end behavior of both of them. So make a curve that kind of looks like that. Let's just repeat the pictures we had before. So these were the 2 pictures we showed before, polynomials, if you remember. So when you talk about in behavior, you're literally going to describe what the graph is doing to the left and to the right. Okay, so I'm underlining to the because it's not from the left, it's to the left. So in other words, as I travel to the left, what's my graph doing? As I go to the left, the graph is going up or is it going down? It's going down, so we use the terminology rises and falls. So since it's going down, we use the word falls. Okay, but as we go to the right, what is this graph doing? It's going up, right? So yeah, we use the word rises. So on your homework, it's literally going to have a couple questions like this where you just like pick a multiple choice option for what you're saying the graph is doing. But what do you notice about this graph? What do you notice about to the left and the right, actually? They're both going down, right? So we would say that the graph falls for both of them. So if we have a graph already, I think that's really pretty easy to tell. Okay? But what if like we don't have a graph? What if we have an equation and we're trying to get a graph? That's actually the general gist of what we're doing today. Okay, well, there's something called the leading coefficient test. This is something you're going to need to know. That's why I put a star by it. So notice I didn't put a star by any of the other definitions really today other than some of the explanations, but none of the other definitions got starred, which means this is one that you really need to know. And so the leading coefficient test just tells what the graph's in behavior is going to be. So maybe we don't already know what the graph is, and it's based on two things. It's based on the degree, and it's based on the leading coefficient. Okay, those two things are going to tell us what the graph is going to do at the ends. Oh, I did. Yeah, thank you. So this should have said to the left and then to the right. So good catch. Okay, so let's run through the options. There's not a whole lot of options if you think about it. They're either going to go up and down in either direction, or they're both going to go up, or they're both going to what? Go down, right? So there's only actually 4 options. Okay, so let's talk about all 4 of them. So if you have an odd degree, so anything that's odd, and a positive leading coefficient, then the graph is always going to do this for the end behavior. It always falls to the left and rises to the right. So the gist of that is if it's an odd degree and a positive leading coefficient, then it falls left and rises right. So we'll do some examples of this in just a minute, but we're just going to get the 4 cases out of the way. All right, so we can also have an odd degree and a negative leading coefficient. So I'm going to stop there for a minute. What do you think happens when I do the same degree but I change it to a negative? It's going to like change direction, right? It's going to be opposite of what we said in the first one, right? So if you know the first rule, then you kind of get the second rule for free. Okay? So the graph is always going to do exactly the opposite of what we said. So it's going to rise to the left and fall to the right. So odd degree, negative leading coefficient means we rise to the left and we fall to the right. So if you know rule number 1, you kind of get rule number 2 for free. All right, so rule number 3, or option number 3, is what if you have an even degree, and we'll start with positive first, and a positive leading coefficient. If you think about it, we've already covered both ways of it going different directions, right? So what do you think is going to happen if you have an even degree and a positive leading coefficient then? Yeah, the graph's going to go up in both directions. So the graph always rises both to the left and to the right. So I think if you really think about it, that one's a little more obvious than maybe the first one. But then again, if you know that one, I say you know the final one, right? What's the only category we haven't covered yet? Well, we already did odds, I think, right? So we need to go even, but switch it to what? Negative, right? So we have an even degree and a negative leading coefficient. Then what do you guess? If you read rule number 3 and you make it opposite, what are you going to guess? It's going to fall in both directions, right? So there are 4 cases, and yes, I want you to know all 4 of them, but I say if you know 2 of them, if you know rules 1 and 3, you can just make them the opposite for rules 3 and 4. So let's underline the important part. If it's even and negative, it falls both to the left and to the right. Okay, so let's do our first kind of full-blown example. So right now, all we really know how to do is the end behavior, so I don't want you to do anything else with these 2 polynomials. So we're going to do them side by side. So let's say that I've got this one. And then this one. Okay, so how do we know they're both polynomials, first of all? They have what kind of exponents that we talked about? Positive whole numbers. Even this guy, right? It has positive whole number exponents, just written a little bit weird. All right, so what 2 things do we need to know to find end behavior? We need the degree, and we need the leading coefficient. Yes. Okay, so what is the degree? That's pretty easy to pick out on this one. 7, okay? And the leading coefficient is what? The number in front of that, x to the 7th, which is 3, okay? But the significant part of this is we care about the fact that this is odd and that this is positive, okay? We don't really care that it's 7, we just care that it's an odd number of some sort. We don't really care that it's 3, we just care that it's a positive number of some sort. So notice this is odd and positive, so go back up to your 4 cases. Which case does that apply to then? The first one, right? So what does that mean about the graph? The graph falls which direction? Falls to the left and rises to the right. So I might not know what that graph is doing in between those ends, but I know what it's going to look like at the end. Yes? Say that again? That's just an equal sign. Like I wrote it as a positive 3. Like It's just 3x to the 7th. It's not negative 3. So, yeah, maybe you see the equal sign and are saying that's a negative, but that's this one. This one is a negative number, but this one's not. So let's do part B. So part B is actually a little bit strange because it's actually written weirdly. And I don't know about you, but I don't really want to FOIL that booger out. Like, it would be a lot of foiling. Can you see that? It would be like x minus 3, 2 of those, and then x plus 1 is how many of those? 3, and that's like a mess, and I don't want to do it, right? So what you need to do is you have to actually think about what would happen if you did. In other words, what would happen if you did a squared times a third power? What would be the biggest power you would have? It would be 5, okay, and hopefully you can kind of see that. So essentially, what do you need to do with the exponents when you're trying to find the degree if it looks like this? Add them up, okay? And then the leading coefficient is just going to be negative 2 because that's the number towards the front. Okay, what's the significance of these, though? I care about the fact that this is odd and that this is what now? Negative. So what does that mean compared to part A, then? It's going to be exactly the opposite, right? The graph's going to rise to the left and fall to the right. So one thing that I would say is a little strange about in behavior is we're not going from left to right. I'm asking you to travel, kind of look at the middle of the graph and go to the left and to the right. Okay, so, and I shouldn't have said it that way, so I messed this one up again. It should have said right there. I don't know why I will keep wanting to write the same word again, but it happens. Okay, so now we've talked about how to know what the graph is doing at the end. So now let's talk about kind of a variety of things we can talk about the graph doing in the middle. So I say you already know how to do this. We've already done this a couple of times, actually. When we talked about linear functions, we did it. And when we talked about parabolas, we did it. How do you always find the y-intercept, no matter what the equation looks like? Set x to 0, yes. Okay. How do you find the x-intercept in general? Set y to 0, yeah. Okay. So the x-intercept, you're going to set y equal to 0. So in other words, you always set the other one equal to 0. Okay. So just so you know, I'm going to put a star here. There's going to actually be a lot more work here than there is here. Okay. And just so you know, there's some other terms we might see for x-intercepts starting in this section. You might see them called roots, but that means the same thing as x-intercepts. Okay. You might see them called zeros. But all of these things are the same as each other as long as they're real numbers. In other words, as long as you don't have anything imaginary or anything janky like that. Imaginary numbers cannot be graphed, so we're really going to focus on tangible, real numbers for this, which should probably make you happy. So the reason I put a star by this is there'll only ever be one y-intercept. How come? We talked about this with parabolas. How come there can only be one y-intercept in any function we'll learn about this semester? And then it's not a function, right? It'll fail what test that was on test 1? The vertical line test, right? So, but x-intercepts, we can have lots of those, okay? So with parabolas, we had at most what? What was the most number of x-intercepts we had with parabolas? 2, okay? And so that's not an accident that the most was 2 and that it was a squared equation. So a polynomial function of any degree, so I'm just going to say of degree n, because n just means it could be anything, has at most n roots. So what does at most mean? It can't go higher, right? But what could it do? Could go lower, okay? So an example would be if you look at that function we were looking at above, the 3x to the 7th minus 4x cubed plus 5x minus 10. What is the most number of x-intercepts I can expect here? I can have at most 7 roots. Slash X-Intercepts. Okay, doesn't mean I'll have 7, it just means I shouldn't have any more than 7. Okay, so with this concept of us being able to have at most the number of roots, we have a concept with each root called multiplicity. Have y'all ever seen that movie, Multiplicity? It's not very good, but it's where a guy like clones himself and keeps cloning himself because he wants people to do his work for him, and then he gets out of control. But anyway, so multiplicity is just how many times something occurs. Okay, so multiplicity of a root is how many times each root occurs. It's not the same as degree. Degree is like one number that describes the whole polynomial. Multiplicity is how many times each root happens. So let me show you an example of one that is already kind of factored for you, but you just have to find every X-intercept and then every multiplicity of each of those. So find the multiplicity of each root. And then when you're done, I want you to tell me what the degree of the polynomial is. And actually, we don't even have to wait till we're done. So let's say that this is the polynomial that I gave you. So before you worry or freak out about how this actually looks like I want it to. It's actually already fully factored for me, and I definitely wouldn't want to factor that guy by myself. Okay. But if I ask you for the degree, do you remember how we do that? Add all the exponents up, right? You even have to include this one. What's the understood exponent for this middle or the second parentheses? It's an understood 1, right? So you can write it in if you want to. Okay, but that's a 1, so I have 6, 3 more is 9, 5 more is a total of what? 14, okay? So I would never ask you to factor something like this, like that's too crazy big, right? But I might give it to you already factored, okay? Because if I'm asking you for the root or the X-intercept, I just need to set this equal to what? 0, okay? And then what do I do with each part? It's already factored for me, so what do I know about each part? I have to set each part equal to what? 0. So each distinctive part of this factored polynomial I need to set equal to 0. And I need to see how many roots I get or how many X-intercepts I get. Okay. So what happens when you get rid of that 5th power? In other words, like you would 5th root it, but it's still going to be what? 0, right? Like 0 to any power is still 0. So that's the only number that would work there. But because of this 5, it actually means that the multiplicity is 5. So you don't have to write this down, but think of it like this. Remember, x to the 5th means this. Right? So how many x's are there then? There's 5, right? So that's why the multiplicity of that root is 5. Okay, what about this guy? What would we get for x? If you add 3 to both sides. 3. Okay, but when you go back up here, how many times did that root occur? Just once. So the multiplicity of this one is just 1. Okay, so you're really just looking at the power every time. What about here? What would be the X-intercept of this guy? Subtract 2, right? So you get what? -2. But come up here, how many of these parentheses would I have if I decided to expand it out? 3. And then last but not least, what would I get for this very last X-intercept? I would get 4, right, if you add 4 to both sides. But then up here, what's the degree going to be? Or what's the multiplicity, not the degree? The multiplicity of this one's also 5. Okay, so notice if you add 5, 1, 3 and 5 together, you get the overall degree, which is 14. Okay? So, not that I would ever give you something like this for you to factor yourself, but how many roots could we have had? Because it was 14th degree. We could have had 14, but we only ended up having how many different ones? 4, but we had ones that were repeating themselves. Okay? But so in the end, I'm trying to let you know that we're really accounting for all 14 roots. It's just we're repeating this one 5 times. We're repeating this one 3 times, and we're repeating this one 5 times. If you add all of those up, you still have a total of 14. Okay? So we're still accounting for all 14. It's just that we have multiplicity issues here. So I want you to kind of jot that down. Okay? Note, if you add all the multiplicities, you get 14, which is the degree of the whole polynomial. Okay, so multiplicity not only accounts for every root that we need, multiplicity also tells us something else about the X-intercept. So I'm putting a star by this. I want you to commit it to memory and know it. But if a polynomial has a 0 with an even multiplicity, remember multiplicity is not the same thing as degree. Then what it's telling you is the graph touches the x-axis at that spot, at that x-intercept. But then it turns around. So even multiplicities are going to touch the x-axis because that's what x-intercepts are, but more than that, they're going to turn around once they get there. So I want to show kind of a basic example here, and then we're going to put kind of all this together in a little bit. Let's say that I asked you to graph this. Now, I say you already should know what the graph of that is based on what we tested on for test 1, right? Why do I say you should already know what that graph is? It's a parabola because of the squared, right? And what is the -3 on the inside telling you? It's going to, well, the other way, right? To the right 3. So we can go ahead and sketch this. And then we'll talk about kind of what it means. It's going to be a parabola that's shifted to the right 3. So here's going to be what it looks like. But notice that if I tried to find the zeros here, I would just set x minus 3 to 0, right? So I would get an x-intercept of 3. But what do you notice about the multiplicity if you go up and look at this 2 here? Since the multiplicity is 2, which is even, then it tells us that the graph turns around. So it's giving you more information. It's not just telling you, hey, it hits the x-axis there, because it does, but it's also telling you what it does after. Okay? So notice, this is my x-intercept, right? And notice that it's turning around at that spot. Because it also could have gone through, right? Some graphs like go all the way through the x-axis, and we're going to look at that here in a minute too. All right, so even multiplicities, those x-intercepts turn around. So what do you guess odd multiplicities are going to do? If they don't turn around, there's only really one other option. What are they going to do? They're going to cross over or go through the x-axis. So if a polynomial has a 0 with an odd multiplicity, and I forget exactly the wording that my math lab uses, but it says something like crosses or goes through or something like that. All of those things mean the same thing. So the graph is still going to touch the x-axis at that X-intercept, because that's what intercepts do. But this time it's going to go through the x-axis. So odd multiplicities go through or cross the x-axis. Okay, so let's look at something like that. So if you know that you have something that looks like x plus 4 parentheses cubed, so once again I'm trying to give you one that we know from before. Okay, so what do you know about this graph? You actually should know what it looks like, or at least be able to picture it or describe it in your head. What's it going to look like because of the cubed? The cubic graph, right? And then what do you know about the plus 4? It's going to shift it left 4. So let's go ahead and sketch it. So we know we're going to go left 4. And then if you remember what the cubics look like, they curve this way and then curve that way. But if we were trying to find out what the x-intercept is, right, we'd set this parentheses equal to 0, and so of course we'd get -4, and that's what we showed here, right? But what do you notice about the power or the multiplicity of that root? It's 3, which is what kind of number? Odd. So rather than it being even, it's odd, okay? So what that means is that the graph is going to do what? It goes through the x-axis or crosses. And notice that's exactly what we show, right? This x-intercept crosses over the x-axis instead of making a turn like it did in the parabola. Okay. So the reason I put a star by the x-intercepts before is we're going to know a lot about the x-intercepts. The y-intercept is kind of boring. There's kind of one of them. They don't really do much of anything. But the x-intercepts, we're going to be able to tell a lot more about them. All right, so I want you to be able to find all the zeros. And the multiplicity of each. And then I want you to describe what the graph does for each 0. So we're not ready to graph it yet, but I want you to describe what the graph would do for each of these. Okay? And so let's say that I give you this polynomial. X cubed plus 10x squared plus 24x. So when you see zeros, what do I want you to kind of think? What's another name for zeros? Yes, x-intercepts is really what it's asking for. Okay, so zeros and x-intercepts are the same. So in other words, what am I wanting you to set y equal to then? Set y equal to 0. Okay. Notice this one's not factored for us, but I think there's something we could do to kind of make it easier to factor, like right off the bat. So what do you notice there is in everything so far? There's an x, so if we divide that out, we'll get x squared plus 10x plus 24. Okay, but now this I know how to factor, or I should, from our quadratic unit. Okay, so remember, I don't even need AC method, right, because this number is just 1. What are the factors of 24 that would give me 10? Well, but that wouldn't work because of the signs, right? We couldn't do 12 minus 2 because then we'd have some minus signs and we have all pluses. So let's try another pair. 6 and 4 would work, right, because of the signs. So x plus 6, x plus 4. So don't forget there are actually 3 parts here, okay? 2 that are obvious, 1 that maybe is not so obvious. This x is still one of the pieces. So I need to set x equal to 0. I need to set x plus 6 equal to 0. And then I need to set x plus 4 equal to 0. Okay. But then when I ask you what the multiplicity is, what do you notice about the powers of each individual separate deal? They're all what? Yeah, all of these multiplicities are 1. So let's write that down and then we'll talk about what it means. The multiplicity of this one's 1, so is this one, and so is this one, because I don't have any squareds or cubes or anything like that. So all of these are obviously the same number, and so they're all odd. Okay, so what does that mean that the graph does for each of them then? So yeah, the graph is going to either turn or cross. That's your 2 options. So which one's it going to do for all of them? It's going to cross for all of them. In other words, it doesn't make a turnaround or anything like that. It doesn't do what a parabola does. So like notice each individual root kind of has its own thing. I guess I really should have finished this one out. What would this root actually be? I just didn't write it. It would actually be x equals -6, right? And this one would actually be x equals what? -4. Okay, this one was already finished, so that's why I kind of hastily looked at the other one. All right, so the last thing, and then we're going to get to graphing some of these guys. That's like our end game for the lesson today. So from chapter 1 stuff or test 1 stuff, remember even functions have y-axis symmetry. I didn't really specifically ask you a question about that on the test because I didn't ask you anything about the graphs. So, but just remember like x squared is even, and the y-axis cuts the graph in half. So I don't want to draw a big graph or even a detailed graph. Do you remember what odd functions have? It was the weird kind of symmetry. Origin symmetry. So remember that looks like this, where like half of it is kind of a rotation of the other half. So the x cubed graph is odd because it has that type of symmetry. And then what did we say about neither functions? Yeah, neither functions have neither of these types of symmetry. Doesn't mean they're not symmetrical in some way, it just means they're not symmetrical in these ways. So neither of these types of symmetry. Because when we're trying to put together a graph of a polynomial, it's really helpful actually if we know if it has symmetry or not. Like if we knew it had y-axis symmetry, we could just graph the right side of it and then copy it on the left side, right? So if we're really trying to sketch what the graph is, then symmetry can help us out if it applies. Okay, so here are the steps for graphing polynomials. You're really not probably even going to need to remember these in any sort of order because my math lab is going to walk you through these steps. And even on the second test where I test you over this stuff, I will list for you what I want you to find before you can graph something. In other words, I'll say graph this by finding blah, 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 blah. Okay. So, but the first thing that you're going to want to do is you're going to want to do the leading coefficient test because the leading coefficient test tells you what the end behavior is. Okay, we just finished talking about that, but remember that was the 4 options. The graph can either rise or fall to the left or right, depending on what we have. So we want to know what the graph is doing at the ends, and then we just work to find out what the graph is doing in between. Okay, so we want to find the y-intercept by setting x equal to 0. we want to find the X-Intercepts by setting Y equal to 0, but that's not all. We also want to find the multiplicity and what the graph is doing at each X-intercept. In other words, there's more information to find out here. So we want to tell what the graph is doing at each root, not just what the roots are. Okay. In other words, does it turn or does it cross? The fourth thing we want to know is there a symmetry hint that might help us? Okay. And remember, we can do that by determining whether it's even, odd, or neither. And honestly, I'm not going to spend too much time on that because that's just kind of something helpful if it's there. If it's not there, we're not going to worry about it. So I'm going to put a star by this step because that step is the longest and it does also give you the most information. Okay? And then last but not least, you're going to graph all the info you have. And you're going to choose additional points if necessary. So this is where you have to use some reasoning skills. If you graph and you have enough information and you can tell what the graph is and what it looks like, then you might not need to pick additional points. Okay? But if there are gaps in your graph and you're not sure what it's doing at certain spots, then it means you're going to have to pick some additional points. So all of what we've been doing today has been leading up to the problems we're about to do now. Okay, so if you haven't been writing down the notes, like from here on out is probably the more important examples for you to know. Like if you can do these examples, then you can do the entire section, okay, because it kind of walks you through and reviews all the things we've done so far today. All right, so let's say I wanted you to give me a really good idea of what this graph looked like. And you can use the calculator as a backup tool, but you have to be able to show your work. Okay, so we're going to run through all the puzzle pieces that tell us what the graph is going to be. Okay, so the first puzzle piece is, what does it look like at the ends? Okay, so remember, two things tell us what the end behavior is. They are the leading coefficient and the what? The degree. Okay, so the degree is 4. That's the highest exponent. And the leading coefficient in front of that, x to the 4th, is what? 1. We only really care about the fact that we have an even degree and we have a positive leading coefficient. We don't even really so much care about the numbers. We just care about the fact that it's even and positive. Okay, so what is the graph going to do then since it's even and positive? Yeah, it rises in both directions. Okay, so it goes up in both spots, both places, to the left and to the right. Okay, so that's what the graph looks like on the ends. So now let's look at the Y-intercept. Okay, so we're going to set x to 0 and try not to overthink that. This is usually a pretty quick step because a bunch of stuff's just going to go to 0. So what is 0 to the 4th minus 9 times 0 squared? It's still what? 0. So if you're asked to write it as a point, you could say 0, 0. So I'm going to kind of circle the things you would need to be able to answer on your lab, and then it's going to have you graph it after you're done. Okay, so step number 3. Remember, this is the most lengthy / the most helpful step. It tells us the most pieces of information that we can possibly have. All right, so how do you find the x-intercept? You take the equation and set it equal to what? 0? So kind of like the one we did before, what do you notice we could go ahead and factor out right away? Like, what do these have in common? We could go ahead and make an easier equation to work with.
X squared.
Yeah, x squared, and if we did that, we'd get x squared minus 9. But then I say we can work on this, right? This is one of our special case factoring scenarios, right? So what's x squared minus 9 when we factor it? It factors into 2 parts. Do you remember that from the first week and from your comp test? So what does it factor into? Yeah, x plus 3, x minus 3. So I've got 3 parts. I need to set x squared equal to 0. I need to set x plus 3 equal to 0. And I need to set x minus 3 equal to 0. Because I just take each of these 3 parts, set them equal to 0. All right, so for this one, I just get x equals 0, right, if you square root both sides. But what do you notice about because of the squared? The multiplicity is actually what? 2, which is even. Okay, so this means that the graph turns. Yep. So I'm going to circle all of this. We not only know that it touches the x-axis at 0, but now we know that it turns there. Okay, what 0 or x-intercept do I get here? Negative 3. Okay, so look back up here. At negative 3 or right here at this parentheses, was I squared or anything weird like that? I wasn't, right? So the multiplicity is just 1, just occurs once. Remember, these are 2 separate things. They are very similar to each other, but they're separate. So the multiplicity is odd, which means the graph does what? Crosses. So this is the second x-intercept that I have. And then last but not least, what's my last x-intercept? 3, and what's the multiplicity there? Like, look back up at the factored version. Notice it only occurs how many times? Once, which is odd. So the graph crosses here too. So I'm almost to the point where I'm going to put all this info together. Okay. So step number 4 is just to decide if you think it has symmetry or not. So I don't want to go back and do the even, odd, neither thing. We already did that in test 1. Okay. But just know that it does work out to be even if you go through the process that you were supposed to learn for test 1. So if it's even, what does that mean? It has what kind of symmetry then? Y-axis symmetry. So that's going to help us out when we graph. So I'm just going to circle that, yep, it has some symmetry. Sometimes the answer will be no, it doesn't, and so you won't get the added bonus of kind of having that. All right, so here's the point of the whole problem, is to get a good, decent looking graph when you're finished. Okay, so notice we have we can go out 3 and then we'll go out more if we have to. Probably we'll have to. So now you just go through your list of stuff and you start plotting points, right? We know it crosses the y-axis at 0. We know it crosses the x-axis at what 3 spots? 0, negative 3, and 3. Okay, and we actually know that it goes up in both directions. So at the ends, we know what it does too. Okay, so what's kind of the only thing we're not really 100% sure about right now? We just don't know what it's doing, like in between this and in between that and that, right? Okay, but I say we even know a little bit more, right? We know that it crosses here. We know that it does what? Turns here, and we know that it crosses here. Okay, so I'm going to do this with a dashed line. So this is essentially what I know it does. It's got to cross through, right? But then what's it going to have to do? Because it has to come back up here and hit. So it's going to have to hit like this, right? And then what's it going to have to do again? Because of this turn. It's going to have to come down here and then go up here, right? So what's kind of the only thing we kind of don't know?
How far down?
We just don't know how far down it goes. Okay? So that is where our additional points come in. Okay, so we just need to figure out what it's doing kind of in the middle. So when I say choose additional points, okay, I'm going to choose the one right in between 2 points that I want to know about. Okay, so I'm going to choose x equals 1.5. Why did I choose 1.5? Because what did I want to know about? what the graph was doing in between what? 0 and 3, right? So I'm not going to pick 1 and 2. I could, but if I can pick 1.5, I'll get right in the middle of both of them. Okay? So I'm going to pick 1.5. So how am I going to figure out what the y value is there? It's actually pretty easy. I just plug it in. If I want the y, I just plug it in. So I just find f of 1.5, and you have a calculator for that. So it's 1.5 to the 4th power minus 9 times 1.5 squared. I'm just plugging it into that x to the 4th minus x squared. So to save time, I'm going to tell you what I got. I got negative 18.1875. Let me rewrite that because it's really sloppy. So negative 15.1875. So we wanted to know how far down it went. Okay, and now we know. So in a situation like this, this is what my strong suggestion is for you to do. Just go ahead and mark, hey, here's negative 15, because I'm too lazy and I don't want to count all the way down to negative 15. Okay, and then we just need to go just a little bit under that, right? So 1.5 and then down just a little under. So you already kind of knew it looks like a W shape, but now you kind of have how far down it goes. Okay, but then because of symmetry, what do we know about the left side? Yeah, left side looks the same. Okay, if we didn't know that, then we might need to pick another point on the left side. Okay, but we don't have to do that because we know that it looks the same. So we know it's got to be curvy, and we know it's going to go down just as far. So it ends up looking like a W. And remember, it has to be a curvy W, not a sharp-edged W, because it's a polynomial. Okay, so as long as you do something like this where you say, hey, I knew how tall it was, I just didn't quite want to, label all the way down to 15 or something, then you should be able to do that. Okay, so let's start one more. We'll see how far we can get with it. These are time-consuming problems, but again, we just had to learn a lot before we could get to the point where we were ready to do these. But if you can do these types of problems, then you know all the pieces from this section that I want you to know. Okay, so first thing, we know it's a polynomial, right? Because it's positive whole number exponents. Okay, so the first thing is, again, and my math lab will lead you through these steps, but what's the end behavior? So we need two things for this, leading coefficient, but also degree. So what's the leading coefficient? Well, that's the degree, yeah. So I'll put that there. The leading coefficient is actually what? 1. And I care about the fact that this is positive and this is what? Odd. Okay. So what does that mean about the graph? I'm going to use arrows. So the graph falls to the left, right? You can use the word fall or you can use an arrow there. Okay. And it rises to the right. Okay, so I know what it does at the ends, so now let's focus on what it's doing in between there. So number 2, what's the Y-intercept? Okay, so again, that's usually pretty simple to find. It's a lot harder to do the X-intercepts. So 0 cubed minus 2 times 0 squared plus 0 is just a big fat what? 0. It's not very interesting, but 0, 0 is a pretty common point for it to cross through, so expect to see that fairly regularly. So here's the step I told you to take some care with because it's going to tell us some information that is helpful to us. Okay, so I want to find the X-intercepts, right? And I'm going to do that by setting the equation equal to what? 0, and then seeing what I can do with it. Okay. So notice, normally I don't know how to factor a cubic yet, okay, but I can do something nice to this right off the bat. What can I do? Take out an x. So if I do, I get x squared minus 2x. Be careful about this, you actually get plus 1, right? If you divide x by itself, there's a 1 left. It's not nothing there, it's a plus 1. So the x stays, but